In this video, we are going to look at frequency, period, and angular frequency, and we will also derive the centripetal acceleration, which equals v squared over r. Here we have an object that is moving around a circle at constant speed v, and the circle has radius r. And let's go ahead and define a few quantities here. So we could define the position of this object. We will say from the origin, the position is position r. And we could describe that position r as a vector where it is made up of its x component plus its y component. And so if I draw its x and y components on this diagram here, we have the x component looks like this, and then the y component looks like this. And so we have a right triangle here, and we could also define this angle. It's more useful when dealing with circular motion to describe position as the distance from the origin, which would be the radius of the circle, and the angle from the x-axis. So here what we could do is replace this position r. We could replace each component with a value related to the radius of the circle and the angle. So the x component is equal to r cosine theta, and the y component is equal to r sine of theta. So that's how we could describe the position. So we have an object, it's moving around this circle. The time that it takes to make it around the circle one time is defined as the period. So let's go ahead and write that. So the period is the time to complete one revolution around that circle. And we use the letter capital T to represent period. Frequency is the number of revolutions per second. So it's the number of times that the object will rotate around that circle per second. You've probably seen this quantity measured in your car, for example, because your car has a tachometer which measures the revolutions per minute. And we use a lowercase f to represent frequency. So in our diagram, we represent position with r, the radius of the circle, and theta, which is the angle from the x-axis. And theta is changing, right? And in this case, if the object is moving at a constant speed, then that angle is going to change at a constant rate. But in general, the rate at which that angle changes, we can say derivative of theta with respect to time, that is equal to what we call the angular frequency. And we use the Greek letter omega, lowercase omega, to represent that. So this is angular frequency. And this is the rate of change of that angle. So like I said, in this case, omega is a constant, that rate is a constant. So we could say omega is equal to the angle of the entire circle over the time that it takes to get around the circle, which we called that the period. And so we could replace theta here with 2 pi radians. That's the total angle of the circle over orbital period. So here's one relationship that we have. Omega is 2 pi over t. And also, period and frequency are related. They are the inverse of each other. So period is equal to the inverse of frequency. And so what we could do with omega here is we could rewrite that as 2 pi times the frequency. Okay, we won't use angular frequency a whole lot yet, That will be mostly used when we get to rotation, but we need to talk about it here to derive that centripetal acceleration. And one more relationship to talk about here. We know that the speed is a constant, right? And so we could say the speed here is the total distance traveled over the time that it takes to travel around the circle. The distance traveled would be the circumference of the circle, and the time to make it around the circle one time is the orbital period t. And we could replace circumference with 2 pi r over orbital period t. And we're going to need these relationships later on. Okay, so to start out deriving the centripetal acceleration, let's go ahead and start out with what our derivative is. So acceleration is equal to the derivative of velocity with respect to time. Okay, but we don't know an equation for velocity relative to time yet, but we do know the equation for position. So what we can do first is find velocity by taking the derivative of position with respect to time. So that's what we will start out doing here. And position, we said earlier, so this will be derivative with respect to time of position, we said, is r cosine theta plus r sine of theta. The radius here is a constant, and so we can factor that out of the derivative. So we have d by dt of, we have r times d by dt of cosine theta plus sine theta. So now we're just going to be taking the derivative of cosine theta and sine theta. And if we look at our equation sheet here, then we know what the derivative for sine and cosine are. And let me just talk about this for a second here. So AP gives us these derivatives, and there's one slight difference that we have here. So here we are taking the derivative with respect to x, and that is our variable inside of our sine and cosine function. But in our case, we are taking the derivative with respect to time, and inside of our cosine and sine functions here, we have theta. Now, theta in this case is not constant, right? It is going to change. And theta, so that means that theta is a function of time. It's a function of time. It's going to change as time changes. So the derivative of cosine theta here is not just negative sine theta. What we have to do here is actually take the derivative of whatever function is in the inside of that trig function. So let me just do those one at a time. So the derivative with respect to time of cosine of theta, where theta is actually a function of time, this is going to equal negative sine of theta, and we're going to multiply it by the derivative of that inside function, which in this case is, we don't really know what that function is, so we're just going to write it as d theta by dt. It's the derivative of theta with respect to time. And the derivative with respect to time for the sine function is going to equal cosine of theta times the derivative of theta with respect to time. So we can sub these back into our velocity function since we already did the derivative. And so what we're going to have here now is velocity is equal to r times what we just found. So we're going to have, I'm going to put the derivative of theta out front. So it'll be negative d theta dt times the sine of theta plus d theta dt times the cosine of theta. And what we defined earlier, we said that d theta dt is equal to omega, right? This is the angular frequency. So let's go ahead, just to make things look a little bit nicer, let's replace d theta dt with the angular frequency. Okay, this would be like if we had dx dt there instead, we could just replace that with velocity. It's basically the same thing, but it's the rotational or rotational version of that. So let's go ahead and write that out. And I'm also going to factor that out of this equation here. So we're going to write this as r, and I'm going to factor out the d theta dt, which is equal to omega. So we have r times omega times negative sine theta plus cosine of theta. And that is our velocity equation. And so now to get acceleration, we can take the derivative of that equation, dv dt. And so that is going to be d by dt of everything we just found. So r omega times negative sine theta plus cosine of theta. The r omega, we can take that out of the derivative. So we're going to have r times omega d by dt of negative sine theta plus cosine theta. And so now we're just going to be taking the derivative of negative sine theta and then the derivative of cosine theta. And so we're going to get r times omega. Derivative of negative sine theta is going to be negative cosine of theta times the derivative of theta with respect to time. Remember, we have to take the derivative of that inside function again. And then we're going to have plus a negative sine theta, and then times that by the derivative of theta with respect to time. Okay, and so now what we can do is replace d theta dt with omega again, and we will factor out a negative omega from this. And if we do that, then we can write this as negative r omega squared times cosine theta plus sine of theta. And now what I'm going to do here is I'm going to distribute this r into that equation so that we have negative omega squared times r cosine theta plus r sine of theta. And if we go all the way back to the beginning of this derivation, we have r is equal to r cosine theta plus r sine theta, the position r, the vector r. So we can replace that with the vector r. And so what we end up with is acceleration is equal to a negative omega squared times the vector r. And this is the vector acceleration. So let me explain what this means here. So what this says is that acceleration is proportional to r, but the negative of it, right? The negative of r. And so if we look at r, that's the position. The position is pointing outward. And since we're getting a negative here, then that means that the direction is flipped. So what that means is that acceleration is going to be opposite in direction of r, which we found that in the last video. Acceleration is always going to be the opposite direction of r, pointing towards the center of the circle. And so what we're going to do down here for our acceleration, since we already know the direction, we just want the magnitude of a. And so the magnitude of this is going to be just omega squared times r, and we're going to drop that vector. All right, so a little bit more work here to do. We need to get rid of omega, and we found a few relationships earlier. And what we have here is, first of all, omega is 2 pi over t. So let's go ahead and replace let's just write that down here below. So we have omega is 2 pi over t, and the other relationship that we found is velocity is 2 pi r over t. And so let's go ahead and let's take this equation here and let's solve for the period, and then take that and plug it into this equation here. So if we do that, then we're going to have orbital period is equal to 2 pi over angular frequency. And now we can take this and plug it in for orbital period here. And we end up with velocity is equal to 2 pi times r over 2 pi over omega. And if we do that, the 2 pi's cancel out, and we can bring this to the numerator and write it as omega r. So here's another relationship. Velocity is equal to the angular frequency, or sometimes called angular velocity, times the radius r. And this is our equation sheet, and you can see that's one of the equations that they give you in the equation sheet. Velocity is equal to r times omega. And so now what we want to do here, I'm going to solve for omega. So omega is equal to v over r. And let's replace omega in our acceleration equation with v over r. And if we do that, we get v over r squared times r, and that gives us v squared over r squared times r, which leaves us with v squared over r. So that's how you get centripetal acceleration, is v squared over r. AP will never ask you to do this, but I wanted to go ahead and show you the derivation so that you know where this comes from. But from now on, let's just remember that centripetal acceleration is v squared over r. And the centripetal force, therefore, is mass times centripetal acceleration, which is equal to mass times v squared over r. And they also give you this relationship in the equation sheet. So centripetal acceleration v squared over r, which is equal to omega squared times r.